Units and measures is what we're going to discuss. Why are we doing units and measures? Simply put, I need to answer a question. I need to answer a lot of questions. And I answer them with units and measures. Why do we need them? We need them to say where things happen. Okay? I look up into the sky and I see an explosion in the sky. So I get on the phone to a friend of mine who's over in Arizona and say, hey, I just saw an explosion in the sky. And the first question they're going to ask me is, where? Okay? We've got to agree on a way to communicate location. Okay? What else? We need to communicate size. Was it a big explosion or a little explosion? Well, I don't know. It depends. If you were there at the time, it was probably a big explosion. But from where I'm standing, so that's one thing. Okay? Be able to communicate size. The difference between a Prius and a Ford F-350. Right? There's certainly a difference between them. We have to answer the question that any 3-year-old would ask. How big is it? These are all pretty straightforward questions, right? We need to communicate relationships. Okay. I looked up in the sky and I saw an explosion. Well, what caused the explosion? I don't know. But I was looking over in the other direction. I saw another explosion over that way. What caused that? What's the relationships? If one thing gets bigger, does that affect something else? Okay. As your age gets bigger, does your size get bigger? Well, for a while, you get bigger vertically, and then after a while, you get bigger horizontally, at least in our society. The trick is being able to do it via the gym or via the donuts. Okay. This is supposed to be facetious and funny, but you get the idea here, okay, guys? All right, so what makes a good unit? I need to communicate all of these relationships. I need to be able to tell my friend over in Arizona that I saw this explosion in the sky and this is what happened and so on down that, so we can try to figure out what the heck happened. Okay? My unit of measure must be easy to replicate. When I mean easy to replicate, it means I need to be able to take my unit of measure where I'm at, and my friend in Arizona is supposed to take the same unit of measure where he's at. If my unit of measure is a length of string, is that convenient? Or not? It's convenient for me, but is it easy to replicate? No, it is not, because unless that my friend in Arizona has the exact same piece of string or measured something, then it doesn't work. Oh, and by the way, it gets worse because when I write that scientific paper about the thing that exploded in the sky, I got to say it's 90-something string lengths long. And of course, everybody who reads it goes, yeah, great, what's a string length? So that means I got to start telling everybody what a string length is. Maybe I should just give up and go with a standard, with an easy to replicate unit of measure. I need something that's appropriately scaled. I need something that's the right size. Okay? Can I take my string length to denote the distance to an object out in space? Probably not. Okay? And the big thing is this, it has to be standard. Standardized unit of measure. That means that when I talk about a foot, then my friend in Arizona knows what I'm talking about. Of course, units of measure have not always been standardized. During the medieval times, the units of measure were based upon the king. And if you got yourself a new king, you got yourself a new unit, all of a sudden, hey, wow, the king's bigger, my land just got smaller. Because instead of being 50 feet long, it is now only 45 feet long because the king's got bigger feet. What happens between a French foot and an English foot? You see what I mean? Okay. I use an example of how do you build an ark, but let me give you a different example, a more modern example. Okay. Let me go, pull that out, there we go. Let me go ahead and do a search here on a smoot. And there is a Wikipedia entry for a smoot. What is this? Something just stopped? there is a Wikipedia entry for a smoot. Okay? That looks kind of weird, doesn't it? In fact, it looks even worse because that's the 100 smoot mark. Let me tell you the tale of the smoot. Okay? And I read this directly from the Wikipedia article. History. The smoot is a non-standard unit of length created as part of an MIT fraternity prank. It is named after Oliver R. Smoot, a fraternity pledge for Lambda Chi Alpha, who in October 1958 lay down repeatedly on the Harvard Bridge between Boston and Cambridge so his fraternity brothers could use his height to measure the length of the bridge. To which point, you're probably asking yourself, why? Which is certainly a legitimate question to ask yourself. Because I certainly asked it when I found out about this many, many years ago. Here's the way it works out. If you're up in New England, you know that in the wintertime it sucks when the nor'easters come in and the blizzards blow and all that other stuff. And you want to cross this bridge between Boston and Cambridge over the Charles River. You're walking along with your head down, the wind blowing. These guys at this fraternity decided we need to mark out how far we are from the end of the bridge. So again, 1958, they said, pledge class, put marks on the bridge so we can figure out how far we are, but you cannot use a yardstick. So the pledge class got together, they put their arms around each other, grabbed the one guy and said, Oliver, you're it. So he lay down on the ground, and they put, where his feet were, they put a 0 mark. And where his head was, they put 1. Then he got up, laid down, and put down 2, and so on down the line. And they kept marking the bridge as it went along in these units of length called smoots. And by the time they were getting to the end of it, they had to pick Oliver up and put him down because he was getting tired and all. It turns out, okay, so the unit of length, the smoot, well, Oliver was 5 foot 7 inches tall, so that's the unit of a smoot, is 5 foot 7 inches. The length of the bridge, which is pictured at the end, the length of the bridge at this point right here, is 364.4 smoots plus or minus 1 ear. See, plus or minus 1 ear. Okay. Everything make sense there, guys? Kind of. Is it a convenient unit? Sure, as long as you got Oliver around, you got yourself a convenient unit. Okay, is it appropriately scaled? To measure the bridge, I mean. Yeah, it certainly is. Okay, is it standard? Oliver's probably a one of a kind. Yeah. Okay, by the way, a little bit of an aside. Oliver Smoot graduated from MIT with the class of 1962, became a lawyer, and then became the chairman of the American National Standards Institute and the president of the International Organization for Standardization. In other words, he was in charge of weights and measures in the United States. The symmetry is almost delicious, isn't it? Okay. So I point that out because, again, a smoot is a good unit. Unfortunately, it's not one you really can use over and over again unless you happen to have a stick that is 1 smoot length. And then we all have to kind of agree that we're going to use it. Okay? So what we need to do instead then, what we need to do is base our measurement system off of some natural phenomena. All right, here's another bit of an aside. We're going to start off with fundamental quantities or properties. Now, what do I mean by that? What I mean by fundamental quantities and properties is the same thing when you guys took geometry in high school. You had to prove everything, didn't you? You had to prove everything, but you couldn't prove everything because you had to start off with something that was already true. Right? You had to start off with the axioms and postulates. And from the axioms and postulates, you say, okay, we're going to say these are true statements. From this point, we're now going to prove everything else. Okay? So what we're going to do is we're going to take fundamental quantities or properties of the universe, say these are going to be these properties of the universe we're going to base our standards of measure on. And then we're going to build from there. First one is the unit of mass. What's our definition of mass? What is mass? Yes? How much something weighs? That's a unit of force. So weight is a force. It's not so that's not mass. Yes? Anything that takes up space, if it takes up space, that's volume, not mass. Yes? How much matter an object has, that's about as close as we can get. I define it a little bit more fuzzier for our working definition, how much stuff an object has, because I can't even define what matter is. You know, it's those questions that a 3-year-old asks that nobody can really answer well. What is matter? You see what I mean? That's a tough one. So we're just going to stick with a fairly fuzzy working definition, which says that an object that has more mass has more stuff. Sometimes it's easy, like for example, if we look on the periodic table, we know that hydrogen has less stuff than uranium. That's because uranium's got more protons and neutrons and electrons. But we also know, for example, that a proton has more stuff than an electron. A proton has about 2,000 times more mass than an electron. I don't know what that stuff is, I just know that there's more of it. Okay, so that's why mass and weight are two different things. Weight is how that stuff is pulled, but mass is that amount. Does that make sense? Okay, so we're going to start off with the amount of stuff, mass. Next, we're going to have length. That's related to your statement where you said how much space an object takes up. Well, not quite. It's how much an object goes in one direction. I'm not talking about change in position. I'm talking about the size of the object in one direction. We call that length. Okay, so for example, if you take a look at a road, well, yes, we certainly are concerned with the width of the road. It's the difference between a 2-lane highway or even a 1-lane highway I've driven on in Scotland. That was fun. And an 8-lane highway on the interstates, or even the 10-lane highway in some places like Houston or Los Angeles or Dallas, right? But what's the important thing? It's not the width of the road, it's the length of the road, because the road's got to go from point A to point B, okay? The next thing, which is another property of the universe, I'm listing two things, but I'm interested in only one thing, it's time. Time is what allows motion. Time is what allows processes to occur. Time is what makes the universe interesting. Otherwise, if we didn't have time, the universe wouldn't change. Okay? The last item that's there, that's electrical current. And we'll deal with electrical current in the second semester. Okay? So for our purposes, for right now, all we're really interested in as our fundamental properties is mass, length, and time. Okay, now, again, we have to have convenient units of measure. We have to have appropriately scaled units of measure. We have to have standardized units of measure. And so we're going to standardize our units of measure because we're all going to agree as a people, that is to say, especially the scientists, that we're going to use this system, and it's called the Système International. It is not called the SI system because that's redundant. That's like ATM machine or ITC cycle. Okay. SI, not SI system. Système International system. You see where I'm going here? Okay. The SI is based on the metric system with some minor changes. First of all, the mass is not going to be based on the gram. It's going to be based on the kilogram. What is the kilogram? No, it is not. The kilogram is a brick that is in Paris. The kilogram is not 1,000 grams. The kilogram is a brick in Paris, and we say that's 1 kilogram in mass. Everybody, we all agree that's the mass. That's a kilogram. And so a gram becomes 1/1000th of the kilogram. So you see how the gram is based on the kilogram and not the other way around. The metric system, that was different. I agree. Okay. Oh, by the way, that's fairly arbitrary, isn't it? That is fairly arbitrary. And that's one of the issues that scientists are trying to overcome, trying to figure out a natural definition of a kilogram. Question? Okay, the question is that the brick will eventually deteriorate. The answer is not quite. First of all, the brick is made out of a material, platinum iridium, so it is not subject to corrosion. Second of all, it's being kept isolated. It only comes out once every 10 years. And it's kept in an inert gas, again, to prevent corrosion, wear, physical reaction, things like that. Okay? Does the mass of the kilogram change? It does, but not anything that us lay people can measure. But that's one of the reasons why scientists, especially scientists who require very, very high degrees of precision, that's one of the reasons why they want to find a natural definition, similar to what we can for the meter. The length of the meter under the metric system was originally defined as 1/millionth, I believe 1/millionth or 1/billionth, the distance from the equator to the North Pole. Back in the late 1700s, that was the definition. Now we define the meter as the distance that a light wave travels in a specific period of time. So now we have a natural definition because the speed of light is a universal constant. Excuse me. The speed of light is a universal constant. So if we have that speed and we have time, then we know the distance. Okay, so we now have a natural definition for the unit of length. We also have a natural definition for our unit of time. It is the amount of time it takes, and again, we don't need to know these, this is just good to know. It's the amount of time it takes for a specific number of vibrations of a specific energized quartz crystal. Okay. So, we have a natural definition of time, we have a natural definition of length, we have an arbitrary definition of the kilogram, and they're still working on that. Any questions so far? Yes, sir.
Aren't they still working on time?
No, they've got a natural definition. What they got is you take this crystal, and then you put it under certain conditions where it vibrates. Now, you start the stopwatch to see how long, and start counting the vibrations. When you get to a certain number, that's defined as 1 second. So you see, we have a natural definition, a natural phenomenon that is very reliably replicated. No. Well, there's still some uncertainty as far as the measurement, agreed. But it is very, very precisely measured. We're talking about 18 decimal places. Okay? The last one, the unit of current, the ampere, we'll talk about that in the second semester. Okay? Next, scaling. I mentioned before. So, right now, is it convenient? Well, it depends. Certainly is, for example, meters. I got meter sticks all over the place. I got kilograms all over the place. Why are we using the kilogram and not the gram? That's a good question. The answer is that the SI units are human scaled. They're scaled so that you can sense changes of them relatively easily. For example, what is the difference between 1 gram and 2 grams? Can you feel the difference? Put 1 gram in one hand, 2 grams in the other hand. Can you feel the difference? Probably not. But can you feel the difference of a kilogram in one hand and 2 kilograms in the other hand? 1 kilogram is about 2.2 pounds of weight. 2 kilograms is almost 4.5 pounds of weight. You should be able to feel that difference. So that's a human scaled. And just to reinforce that, average person has a mass of around 70 kilograms. Why do I give you this sense of scale? Because oftentimes when you're calculating a problem, you come up with an answer, and you have to determine whether or not that answer makes sense. So if you're calculating the mass of a sparrow and you come up with 300 kilograms, does that make sense? No, it does not. It does not make sense that a sparrow would be 300 kilograms in mass. Okay? 3 kilograms makes a little bit more sense, although it's still pretty heavy. That's a 10-pound sparrow. That's more of an owl than a sparrow, yes? Okay. So you see what I'm getting at is develop a sense of scale with our units of measure. You already have that with the English system, feet and inches and yards. So start developing it with the SI by practicing using that. Okay, meter is about 1 yard. That's easy enough to do. An adult is between 1.5 to 2 meters in height. Of course, we all know that the football field is 100 yards. Anybody who's run track knows that a 440-yard track is almost equivalent to a 400-meter track. Off by only about 1 or 2%. Very close on that. Next, the second. That is about the time between 2 heartbeats. In fact, when Galileo was doing his experiments on motion, he was using a song to measure. He was using a song to measure time. He would go bump, bump, bop, bop, bop. He'd sing this song, and he'd use the downbeat to keep time. Precise? No, but easily replicated. Able to show the relationships. 1 hour is equal to 3,600 seconds. That's because we have a definition of the second. The definition of the minute is 60 seconds. Definition of the hour is 60 minutes to the hour. So the hour is not based upon the day. The day is based upon, it's not, the second is not based upon a day. Day is based upon a second. In fact, part of the problem is we can't even agree upon what a day is. It sounds kind of a little bit of an aside, a little tangent. Astronomers actually have two definitions of a day. The first one's called the solar day. The solar day is the time it takes for the sun to go from local noon to local noon, from directly overhead to directly overhead. That's called a solar day. It averages around 24 hours. They also have what's defined as the sidereal day. It's spelled out sidereal, but sidereal day. That's the time it takes for a specific star to go from overhead to overhead. That's different. That's a little longer by about it's a little shorter by about 4 minutes. That's because in the time it takes for the Earth to rotate one rotation, the Earth has also moved almost a degree in its orbit around the sun. So the star has changed position relative to time. That's why the constellations look different over the year. Okay? So the sidereal day is one length. It's about 4 minutes longer than the solar day. A little bit of, or excuse me, 4 minutes shorter than the solar day. I'm sorry. So that's just a little bit of a side. Okay, table 1.3, that is going to be, that is a table of scale of the of length and of mass and of time. So again, if I ask the question, if you've got yourself a 10-kilogram gorilla, what do you have? No, not 10 pound. Yeah, but what do you got if you got a 10-kilogram gorilla? A very small gorilla. Yeah, you probably got yourself a newborn. You see what I mean? Get a sense of scale. Speaking of scale, can we use those particular units of measure all the time? Maybe. Okay. Can units be too big or too small? Yes, they can. For example, I want to measure the distance from Marion to Birmingham in meters. Can I do that? Is it physically possible? I'm talking from a theoretical standpoint. For me to take a meter stick and measure the distance from Marion to Birmingham? Probably, yeah, you can easily put the stick on the ground and keep following it over and over again, except for one problem. Where's Marion? Better question, where's Birmingham? What I mean by that is not the location of the cities, it's where do I put the meter stick down to start measuring in the first place? Do I start measuring from where I'm standing here, or maybe from the back of the room over there? Or do I start from City Hall or the county courthouse? And let's take a look at Birmingham. Where do I start? Where do I end? Do you see where we're going here? The problem is I can't define, it's too nebulous. It's a blob, if you will, so I can't figure out where to stop measuring. So I'm going to need a larger unit of measure. It makes no sense for me to get all this uncertainty because I don't know where to start or stop. What if I'm trying to measure how big an atom is? Can I take a meter stick and measure the length of an atom? Well, not directly, but the other issue is that the length of an atom is about 1/trillionth the size of a meter. That's really, 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 really small. Put a lot of reallys, you know. 12 digits. That's small, small. So we're going to need ourselves a smaller unit of measure that's more convenient. I mean, after all, there are some times when you measure lengths in feet, and there are other times when you measure lengths in inches, because inches make more sense to use than feet. So we need a smaller unit, and so we're going to do this. We're going to scale our units by using powers of 10 prefixes. You guys have already had a taste of this in chemistry class, yes? Okay, so I'm going to reinforce a lot of stuff that you see already. Let's start off with this. To develop the different scale, all we got to do is take a power of 10. For example, if we have, instead of taking a meter, I want a bigger unit of measure. Let's say 1,000 meters. I'm going to make a unit of measure based on 1,000 meters. Now, 1,000 meters is 10 to the 3 meters, 3 zeros. I'm going to assign a prefix to 10 to the third. And that prefix happens to be kilo. So now all I got to do is take 1,000 meters, turn that to 10 to the third meters, now replace the 10 to the third with kilo, and it becomes 1,000 meters becomes 1 kilometer. You see how that works out? So for example, if I have $6 million as an example, $6 million. Okay? What's my power of 10 for that scale? 10 to the what? 10 to the 6th. So I have 6 times 10 to the 6th dollars. Now I'm going to replace that 10 to the 6th with the prefix. That prefix for 10 to the 6th is mega. And so it becomes $6 million is 6 mega dollars. See how that works out? Really easy to do. Let me give you another example. Oh, by the way, table 1.2, in the reading, that gives you all those power of 10 prefixes. I expect you to memorize them. Not necessarily because I'm going to test you on them, although there are going to be, this first test I will ask a couple of questions on those. But from this point on, there's going to be some problems where I'm going to give you scales, like for example, centimeters, nanometers, megameters. You're going to have to be able to do the conversions. Okay? In other words, know the language. Let me give you an example. What do you got if you've got yourself 1 million phones? Do the power of 10 prefix. What do you got? No, that's 1 million phones. Ten to the 6th phones. 10 to the 6th is what number? Write it out. Write it out and see it. 10 to the 6th, that's 1 followed by 6 zeros. What do you got?
I thought 1 to the 6.
What does that say? Then what is 10 to the 6th phones? No. Write it out. All right, 10 to the 6th. 10 multiplied by itself 6 times. 10 times 10 times 10 times 10 times 10 times 10. What do you got? There we go. You see where we're going here? Don't look at that as this is the number of zeros after the 10. Look at it as this is the number of zeros after the 1. Okay? Does that clear that up? And if you're having trouble again, just do the multiplication. Do the 10 times 10 times 10 times 10. Okay. So what have you got, though? What's my unit of measure I've got? Yes? I got what? 1 megaphone. Exactly right. That is 1 megaphone. Okay, I saw some people groan already. What do you got if you have 1,000th of a peed? Yes? Nope. It's a millipede. Correct. 1,000th of a peed is a millipede. Now you're looking at me going, oh, could it get worse? Yes, it can. What do you got if you got 10 cards? Excuse me? A deck of cards, correct. So now comes the exercise. You see a number of whiteboards here. I want you to get together in groups. For example, you 3 work as a natural group. You 4 are a natural group. You can join them. There's a natural group there. There's the 4. You 3 together. You see you've got whiteboards there? Work together as your groups. I want you to each come up with 3 of your own silly, punny units of measure. Okay? Let's see what kind of imagination we have. Let me bring up table 1.2 so that you can see what those powers of 10 prefixes are. There they are right here. Oh, here we go. So if you want to get up and take a look, I'm going to step out, give you guys a chance to work on it some more, and I'll give you about 5 minutes to come up with something, okay? Okay, so we had a pretty good number of fanciful things. Again, it's to get you into the table so you can get more familiarized with those powers of 10. powers of 10 prefixes? Guys, it's going to be important because many of the problems you're going to get in terms of milli or kilo or giga, and you're going to need to be able to do unit conversions. Speaking of unit conversions, let's talk about that. I realize I'm repeating what you guys have already learned in chemistry, which tells you how important we think it is, both Mr. Berry and I, how important we think this is. Unit conversions work this way. Convert 55 miles an hour into meters per second. Okay, so how do we do that? Do this every time. Paper is cheap. It's going to be really tempting for you as time progresses to try to do it on the fly, either in your head or on a calculator. And invariably what you're going to do is you're going to misuse a conversion factor. Let me give you an example of what I'm talking about. Okay, so we know, for example, that there are 3 feet to 1 yard. Okay, that's an equality. Those are alike. Those are the same thing. It's an equal statement then. So if I make a ratio out of it, if I make a ratio of 3 feet to 1 yard, what is that ratio equal to? 1, exactly right. Now, if you're having trouble visualizing this, try it this way. If A is equal to B, then what does A over B equal to? It has to equal to 1. So that means I could write my conversion factor as a ratio of 3 feet to the yard, or I could also write it as 1 yard is to 3 feet. Now, why do I do it that way? Because I'm going to treat the symbols for the units of measure algebraically like variables. For example, if I have x times x, what do I have? X squared, correct. If I have x divided by x, what do I have? 1. So that means I've just canceled out the x. You see? So what I want to do is I want to take my unit here, 55 miles per hour, and I want to multiply it by something so I can cancel out the hours and miles and leave behind meters and seconds. For starters, let's convert the hours. Okay, what's a useful conversion factor on hours? Yes, it's over back here.
3,600 seconds.
Okay, let's go ahead and break it down into 2 steps instead of just 1 if we don't have it memorized. We'll do 60 minutes to an hour. Now, do we want to put the 60 minutes over 1 hour, or do we want to put 1 hour over 60 minutes? 1 hour over 60 minutes, because we've got an hour in the denominator for our original measurement. We want to put the hour in the numerator in our conversion so it cancels. And then the next step would be to do the same thing with the minutes. And so we would get 1 hour to 60 minutes times 1 minute to 60 seconds. That way, when we do the cancellations, it gets rid of the units we're not interested in, leaves behind the units we are interested in. Okay? We could write 1 minute to 60 seconds or 60 seconds to a minute. Well, we got to look at our original calculation to see where we need to put it. This is the reason why you want to write it down, because it is too easy to put 60 over 1 instead of 1 over 60 if you're trying to do it on the fly. It's even more important in chemistry, because in chemistry you're still dealing with measures like grams, but you got grams of carbon dioxide, then you got grams of oxygen, then you got grams of carbon, and those are going to be different things altogether. That's why you have to write this stuff down. Do the prep beforehand before you mash the buttons. Speaking of doing the prep, we still got to get rid of miles, don't we? Okay? So what we need is a unit conversion factor for miles. Well, when I look it up, I found a conversion factor of miles into kilometers. 1.609 kilometers to the mile. Okay, great. That cancels the miles, but that leaves behind kilometers. I need meters, so I've got to convert kilometers into meters. Good news, this is where the power of 10 becomes real easy. I put the kilometers in the denominator, so I got 1 kilometer. In the numerator, all I got to do is change the prefix from the prefix to the power of 10. So I change it from kilometer, from kilo, to 10 to the third. It becomes 10 to the third meters. you see how handy the power of 10 prefixes are? That literally will give you the unit the conversion factor you need. From that point on, we go ahead and do the cancellations. We're left behind with meters over seconds. Hooray! Let's rewrite it by gathering the like terms. Each of these terms are going to end up being just numbers, so we get 55 times 1.609 times 10 to the third meters divided by 60 times 60 seconds. And now we let the button mashing begin. You see what I mean? You do the prep work, it makes it easy to do the conversion. Easy enough to do, you'll get plenty of practice doing that. But what happens if I throw, oh, by the way, 24.6 meters per second is what turns out. And so, since we've got 3 significant figures going in, we should have 3 significant figures coming out. Easy enough, right? Okay, you'll get plenty of practice doing that. What if I'm dealing with volumes? There I got 500 cubic yards, and I want to convert them into cubic meters. Why? Because I built my plan in the US, but I'm in England, and everything is in metric. Okay? So that means I got to figure out how much concrete do I need to buy. All right, again, we start the same way. 5.00 times 10 to the 2 cubic yards over 1. What do I need to do now? Yes? Okay, yes, we could do that. We can make it a little bit easier. Yes, we can do yards to feet. And we can do feet into meters, for example. Okay, we can look up conversion factors. In fact, you could do something like say, hey, Google, how many feet are in a meter? Hey, Google. Sometimes it works. But Google is great for doing that sort of thing. So is Siri, by the way, which is why I don't allow phones inside the test time, right? You guys need to be able to do it by hand first. Then you can use your other stuff along the way. But anyway, but here's our problem. Remember I told you I want you to treat the units of measure as algebraic variables. So as far as algebraic variables are concerned, how many yards do we have in the numerator in our... We've got 3 of them. We've got 3 symbols for yards. How many do we have in the denominator in our conversion factor? 1. We're not done yet, are we? Because if we do this, we're going to end up with square yards per foot, or square yards times meter. Well, that doesn't give us the answer, does it? So what do we have to do? We got to cube the whole thing. See what we're doing? Or you can do your unit conversion 3 times. This times this times this. Do it 3 times. But if we cube it, that means we cube 3 feet. That becomes 27 cubic feet. This turns into 1 cubic yard. This turns into 1 cubic meter. And then we're going to get somewhere around, called 37 or 30 cubic meters. Or excuse me, 30 cubic feet. Or some number like that. Then we can do the cancellations because then our cubic yards will cancel with the cubic yards to give us 382 cubic meters. Now, does this answer make sense? Does it make sense that we're going to have somewhere around 400 cubic meters when we had 500 cubic yards? Okay, does it make sense? When you consider that the meter is a little bit longer than the yard, then it makes sense that if I have a certain number of yards, I'm going to have a somewhat smaller number of meters, but within about 10% or so. Okay, so if I have 500 cubic yards, then it makes sense I'm going to have an answer somewhere around 400 cubic meters. What happens if my answer was 4,000 cubic meters? Now my answer doesn't make as much sense. Get a sense of scale, and that's going to tell you whether or not you're in the right ballpark or not. We'll talk more about sense of scale and ballpark figures, I believe, next week. Therefore, when you use this method, always include your units in your calculations. Don't just write the numbers down. Write the numbers and the units, because that will tell you where you need to put your conversion factors. Okay? Always use this method. Don't try to do it in your head. After a while, there's going to be some times when you will be able to do it in your head. You know, meters to kilometers is relatively simple. Move the decimal place 3. That's relatively simple. But if you get in the habit of always using this method, especially in chemistry, then you really can't go wrong. Okay? Any questions? Any answers?